In this tutorial, we are going to start with dimensions and units. One of our objectives was to study dimensions and units. And since we saw all the properties related to the fluids, they all had their SI what? The SI units. So we have to know something about units. So properties are expressed in terms of number of basic dimensions. That's we have all the dimensions which are quantified in their basic unit. So this we already know is very simple, that the length is related to the unit meter, mass for kilogram, time is expressed in seconds, temperature here in this course we are going to take Kelvin, electric current, ampere, and amount of light, candela, amount of matter or substance, that's the mole. So these are the basic units where we will derive other fundamental units, and we are going to use them a lot in this course. Are you okay? Sometimes we may use the fundamental units, example those combining two or more primary units, which is going to help us a lot. So let's look at the temperature scale. Temperature scale. In fluid mechanics, we are going to do most of our analysis using what? Temperature. Pay attention here. Most of our analysis is going to be based on temperature. So here are the conversion. Most of the times, if we are working, we should work in either Kelvin or Rankine. Kelvin or Rankine. Are we good? So if that's the case, then if a temperature is in degrees Celsius, assuming a question gives you temperature in degrees Celsius and you want to work in Kelvin, how do we convert? Therefore, if we are to convert any temperature from one of the scale or convert to any other form, let's assume in a question we were given temperature in degrees Celsius, we are going to work in Kelvin. This is the conversion. You add 273.15 to the degrees Celsius to get it in what? Kelvin. Again, if it is in Fahrenheit and your working should be in Rankine, therefore you should add 459. Mostly we use 460 approximately. We add it to the Fahrenheit to get the Rankine. And if it is in Kelvin, 1.8 multiplying the Kelvin will give you Rankine. Also, you have it in Celsius and you want to convert back to Fahrenheit. 1.8 multiplying it plus 32 will give you back to Fahrenheit. What we are saying here is that for temperature change in temperature of a Kelvin is equal to change in temperature of what? Degrees Celsius. And it's true. Are you okay? If I have one temperature of, let's say here is Kelvin, here is Celsius, and I have 160 and I have 140. Are we good? If I convert this 60 to a Celsius, let's say X1, I convert this to a Celsius, say X2. The difference between this is the same as the difference between that. Are we good? If you like, use a conversion, convert 60 to Celsius, 40 to Celsius, and find the difference. That the change in temperature is equal. For Rankine to the change in temperature of Rankine is also equal to the change in Fahrenheit, and that's interesting. So pay attention to the temperature scale. We will be using it in our tutorial section. Surface tension. So as we are studying fluids, let's pay attention to surface tension. How does the surface tension affect our work? How is it important? As engineers studying fluid mechanics, how do we go by it? And capillarity, we will also tackle that. So the molecules at the surface of a liquid have greater attraction for each other than they do for molecules below the surface. Are you okay? So if for a container containing a fluid, like liquid fluid, the molecules at the top have greater attraction. They attract each other with a greater force than those below those surfaces. Are we okay? The surface behaves as it were a skin or a membrane stretched over the liquid mass. So as they attract themselves with a greater force, they now act as if they are a membrane or a skin. They are trying to form a solid layer, and that's what we mean by surface tension. Are we okay? So the molecules attract each other, meaning the force of attraction between each two is greater. So they are approaching somehow a skin or a membrane or a solid entity. Are we good? And that phenomenon helps us in many engineering applications. Are we good? That's what we call surface tension, the ability of the surface of a liquid to behave as if it were a membrane or a skin is called surface tension. Because of the membrane effect, because of this effect, each portion of the surface exerts tension, are we good, on adjacent points of the surface. What we mean is, since each particle is trying to attract the opponent, and the opponent is attracting the opponent, meaning they are going to be tension between them. Are you okay? So when you take these two portions, attracting themselves, these two portions, now as this is attracting that, this one is attracting the one in the middle, there will be tension between them because each one wants the other for itself. Are we good? That's why we are saying there will be a tension exerted between adjacent portions because of the membrane effect. This is what we call surface tension. The tension acts in the plane of the surface, yet it only acts at the surface. The magnitude of the tension per unit length is defined as surface tension. So, for water-air surface, the surface tension is given as 0. Put this aside, 0.073 Newton meter. Meaning for water, we are considering water-air surface, meaning a surface of water exposed to what? Air. Exposed to air. The surface tension of the molecules can be estimated at 0.073 Newton per meter. Meaning this Newton force is acted per each meter of the surface. We can calculate for the surface tension anyway. So surface tension force, the surface tension force is given as the surface tension where L multiplying the L. L is the length over which the surface tension acts. So therefore, if from this equation, surface tension, this is given as the force along the interface over the length of the interface. Are we good? The force along the interface over the length of the interface. So once you know the force acting between the particles exposed toward the surface and you know the length, you are good to calculate for the surface tension. Let's see some applications of the surface tension. The concept of surface tension has been used to explain several commonly observed phenomena. We see many phenomena in our daily activities which needs to be explained, and it can be explained only from the idea of what? Surface tension. Example, a steel needle will float on water. That's interesting. For a steel needle to float on water, if placed gently on the surface, this is due to the surface tension force that supports the needle. Are we good? Under normal circumstance, a steel needle should have sunk when dropped into water. But this can float if we gently place it on the surface. Are we good? Let's make some analysis here. We place it gently on the surface and the surface can support the steel needle. Are we good? Because when you gently place it on it, the force of attraction, the surface tension force, won't be broken. But assuming I leave it from a height and drop it inside, it's from here to, and it is going to be dropped inside at a height with some amount of gravity acting upon it. It is likely to break the surface tension force, then enters into at the bottom. Are we good? That's why we are saying the force is so minimal. It's not a large force to accommodate its force. It is what? Moving. So it will definitely break the surface tension and it will be sunk. But if we gently place it, the force is enough to accommodate the needle and it will float on the surface. I hope we understand. So one phenomenon is steel needle floating on water if gently placed explains that it's true that the surfaces of fluids, liquids, have some amount of what? Attraction or an amount of force greater than those below it. Are we good? The capillary action in smaller diameter tube, we will explain that, and the excess pressure is created inside droplets and bubbles. Let's see how we explain these 2 points over here. The capillary action. So water will rise up in a glass tube, and so water is going to rise up in a glass what? Tube. When we insert a tube inside, let's say, a container containing liquid, that's water, it will begin to rise through the tube. Are we good? So this is it. That explains what? Capillarity, the ability of water molecule to rise inside what? Tubes. But mercury will move down. Wow. Mercury will rather move down a glass tube. That's what we call capillary repulsion. If it is rising, we call it capillary rise. So this white surface indicates that there is some amount of water molecule inside this container, and you can see that the water will be rising through the tube. But for mercury, once you drop a glass tube inside it, it will start to drop. Look at where the mercury is supposed to be at normal sense. If it was to be water, it would be getting somewhere here, but the mercury is rather what? Getting down. And that explains the behavior of what? Capillary repulsion. And all these effects are due to what? Surface what? Tension. It helps us to explain such phenomena. Are we good? Cohesion and adhesion. Cohesion and adhesion. Let's look at this. It's also an important factor to consider in fluid mechanics. Throughout this course, it has been reading from the episode 1 up to this episode. Stay with us. The next episode will be full of calculations. We'll deal with all the formulas, all the parameters we've been talking about, and you see the interesting part of the fluid mechanics. So the attractive force between similar materials is called cohesion. And the attractive force between dissimilar materials is called adhesion. So, for example, if I have water molecules attracting each other, then there is a cohesion between them. There is a cohesion. If I have a mercury molecule attracting a mercury molecule, there is still a cohesion. So the force of attraction between similar materials is what? Cohesion. So let's assume that one human being, human beings, there is some gravitational force between us and ourselves. Are we good? So to bring it into simple terms, there will be some cohesion between us. Are we good? So when the materials are similar materials, then there is cohesion. So the force of attraction between water molecules is cohesion. Between mercury molecules is cohesion. But it's called adhesion if they are dissimilar. They are not of the same materials. So here, for example, if there is now water molecules in a container, the force between the water molecule and the container becomes what? The adhesion force. Are we good? So this cohesion force and adhesion force plays a major role, are we good, in fluids. That's why water wet glass, because the adhesion force is greater. There will be some force between the container and the molecules of the water. So as you pour down this water, there will be some left at the edges of the container because they are not detaching. These forces are not breaking, so it will be wet inside the container. But mercury does not behave that. If you pour down a mercury from a tube, it's likely that everything will come out because the adhesion force is what? Is weak. So this explains these two phenomena. Let's look at some phenomena too. Surface called, let's see, water loving. And we also have, why is it that when a drop of water is on the ground, it forms this curved nature? Are we okay? So if water molecules drop on the floor, this curvature is what formed, meaning the adhesion force is greater than the cohesion force. And such phenomena, when the adhesion force is greater than the cohesion force, we call it hydrophilic. The surface is called hydrophilic, meaning water loving. The adhesion, the particles and the surface have greater force of what? Attraction between themselves, and it's called adhesion. But for something like other fluids, they will rather form what? A circle when they are dropped onto what? The floor. And this also is called what? Hydrophilic water heating. Are we good? Hydrophilic water heating. Because the adhesion force now is less than the cohesion force. So the molecules has greater force towards themselves than what the floor is what offering between them. And that we call the cohesion and the adhesion force. I hope this explains the adhesion and the cohesion phenomena to us a lot. Let's look at vapor pressure. What is vapor pressure? We also consider vapor pressure for fluids. The pressure at which a liquid will boil is called its vapor pressure. Very simple. So if during boiling of a fluid, a liquid fluid, at that pressure is classified as the vapor pressure. And it is a function of what? Temperature, meaning the water vapor increases with temperature. Are we good? The more you heat, you apply heat to the container, containing the liquid fluid, its vapor pressure will also start what? Increasing. And at that pressure at which this liquid will begin to boil is called the vapor pressure. Water boils at 100 degrees Celsius at sea level atmospheric pressure of 1 atmosphere. Are we good? So the vapor pressure of water at 100 degrees Celsius is what? 1 atmosphere. Is that good? We will do the conversion from atmosphere to bar to Pascal. Alright, so the vapor pressure of water at 10 degrees Celsius is also found out to be 0.01 atmosphere. Meaning if we reduce the pressure of water to that atmosphere pressure, the water at 10 degrees Celsius will begin to what? Boil. Are we good? So boiling of water now depends on what temperature and what pressure are we referring to. So it is not necessary that at 100 degrees Celsius water will boil. But if the pressure is not corresponding to the actual pressure needed at that temperature, the water is not going to what? Boil. So let's take into consideration. So such boiling often occurs in flowing fluids. or fluids in pipes and in what? Narrow ways. It mostly occurs in those areas. When such boiling does occur in flowing liquids, vapor bubbles start growing in local region of very low pressure. Are we good? And then collapse in region of high pressure. We will analyze this when we are analyzing pipes, flows in other chapters. Very interesting. And that phenomenon is called cavitation. The forming of bubbles at low pressure and collapsing at high pressures is called cavitation. And it's very interesting. Let's look at our last thing in this episode, that's the Newtonian and non-Newtonian fluids. In our studies, we are going to study two kinds of fluids, Newtonian fluids and non-Newtonian fluids. How do we differentiate between these fluids? And remember, if you are dealing with a fluid, you should know what kind of fluid you are dealing with, because their behavior differs from shear stress and differs from the application of anything. So fluids for which the shear stress is directly proportional to the rate of what strain is called Newtonian fluid. Are we good? The shear stress is proportional to the rate of what strain. These fluids are called, because from this we got this formula as viscosity dV on what dy. So fluids that obey these equations are called what? Newtonian fluids. Not all fluids are going to obey this, but those that does are called Newtonian fluids. And example of Newtonian fluids include air, water, and somewhat oil. Are we good? Meaning the shear stress, when you pour them down, the shear stress causing the flow is now going to be proportional to the deformation what made. Are we good? From our basic mechanics, we know that the stress is proportional to what? The strain. Are we good? And Hooke's law, this will be equal to E and that. The same thing happens to Newtonian fluids. The more shear stress we apply on the fluid or acting on the fluid causes the deformation. That's the rate of what? Strain. So any fluid obeying this phenomenon, so the more you increase the shear stress, the more strain the liquid. We call those liquids as Newtonian fluids, or those fluids as Newtonian fluids. And example of non-Newtonian fluids, these fluids do not obey this phenomenon, meaning at some point as you are increasing the shear stress, they will be static. The strain, the dV dy, this is the stress. It is not going to be linear. Are we good? And those ones are called non-Newtonian fluid. Example is toothpaste, paint, and printer's what? Ink. Those fluids are not Newtonian. But throughout the studies, we are going to focus on Newtonian what? Fluids. Throughout our calculation, our analysis in fluid mechanics, everything in this course will be a Newtonian fluid. So let's look at their behavior in diagram form and look at their graph. For Newtonian fluids, we saw that the shear stress is equal to the shear what? Or the rate of strain as that. The rate of what? The strain. Are we good? Where mu is the what? Coefficient of what? Viscosity. So Newtonian fluids obey this formula, and non-Newtonian fluids will violate this formula. So we can see from the diagram that here is the shear, this is the strain, dV on what? Dy. And these are Newtonian fluid, the graph. It is linear. This one is linear. So as you increase the shear stress, you increase it, the strain will be also what? Increasing. So it's linear, directly proportional to the strain. But look at other things, like we have the big hand plastics. They will be at a point where you have to get to a shear stress before the strain begins to what? Happen. There should be some amount of shear stress before it begins to what? Strain. But for the Newtonian fluid, once you start from 1, then the strain will also start from what? 1. But here you have to move to, let's say, at a point of 10 shear before the strain begins from what? 1, which is not linear. And we can also look at this as what? The shear thinning. We can also look at this as the shear thickening. These are not linear fluids, and they do not obey the Newtonian what? Approach. Alright, thank you for watching this episode. We are done with the theory. In the next episode, serious calculations. Check out for about 6 calculations under the formulas we've come across, shear, viscosity, and everything. Recommend this video, share, like, and comment. Thank you for watching.